This video animation introduces the operation and safety aspects of the company's radiography enclosure. The facility is designed to take non-destructive radiographic images of wellhead welds under enclosure radiography conditions. The definition of enclosure radiography conditions means that the radiographic work, which is carried out using radioactive sources, can take place safely inside the enclosure and is totally separated from other work outside the bay, which can continue unimpeded. There is no need for barrier tape, temporary signs, or the closing off of large areas of site while this important work takes place. In order to achieve this, the enclosure contains a number of specific features designed to ensure employee safety, as well as that of our radiographer contractors who will operate the enclosure on behalf of the company. In this short presentation, we will explain the key features of this facility, which are designed to ensure that the radiation exposures are negligible, below permitted limits, and always as low as reasonably practicable. It will also show the basics of how the bay is operated by demonstrating a typical radiographic procedure. Any employees that are unsure about anything related to the bay should always seek clarification with the local Radiation Protection Supervisor, the RPS, or radiography contractors. Please remember that for the purposes of safety, the enclosure will be under the absolute control of the radiography contractors. Therefore, employees will need to seek permission from the radiography contractors if they ever need to access the bay, an example of which might be to crane wellheads in and out of the facility. The enclosure is constructed using two sets of thick concrete blocks which sandwich compacted sand infill. This provides shielding to stop the radiation from coming through the walls. The enclosure is open-topped because it is not practical to have a movable shielding roof and lift wellheads in and out. This is known as open enclosure radiography. One concern an employee may have is the possibility of radiation escaping in some manner over the walls. While a small amount of radiation does scatter from above the bay, the dose is small and represents only about 1/12 of the typical radiation dose received by the average member of the public as they carry out everyday activities. This facility is quite large and has two entrances for general safety. For example, in the case of a rapid exit in a conventional emergency such as a fire. In routine operation, however, only the rear door is used. You will note that there are two labyrinths which ensure that radiation is not present at the doorways. Because of this, the doors do not need to be shielded. To enter the bay, the door needs to be physically unlocked using a key. The design is such that the key is trapped by the door and cannot be removed until the door is locked again. An employee should never attempt to retrieve the key once in the bay, as this can only be achieved by locking yourself in. When the door is opened, it breaks an interlock above the door, which will cause an alarm to sound if operation is attempted with the door open. This interlock provides an additional safety layer in the unlikely event that the key lock becomes disabled. Inside the bay are several safety and operational features. Running around the walls are emergency pull cables that are clearly signposted. If operating procedures are followed, these are not likely to be used. However, in the case of an emergency, pulling one of these would stop the exposure if someone were trapped inside. Mounted on the wall is a 3-light warning system. This indicates one of 3 states: a green safe state, an amber radiation imminent state, and a red radiation exposure state. Next to this is an independent radiation detector that ensures the red radiation exposure sign is always illuminated when the source is exposed. Inside the bay, the wellhead rests on its support. The source projector that houses and shields the source is inside the wellhead, with the control cables for it leaving the bay through a hole in the wall. If a source projector is present, then the illuminated safety sign will show the green safe status. If this sign is not illuminated, then there will be no source present in the bay. When employees are working in the bay, and a source is present, for example, to crane a wellhead into or out of the enclosure, the radiation source itself will be completely shielded within the projector. Protruding from the projector is a tube down which the source will slide to begin the exposure. The ends of this tube are shielded by a panoramic collimator. This is designed to ensure that radiation is only ever projected from inside the wellhead and never through the open end. While the design is such that the bay walls reduce direct radiation levels outside the bay to very low levels, there is still the possibility of a small amount of radiation scatter from above the bay. The material of the wellhead itself provides a reasonable amount of shielding which reduces this. However, to ensure that the reduction is effective for all wall thicknesses of wellhead, an additional movable shielding canopy is provided, which must be used for all radiographic image taking. After exiting the bay, the door is locked and the key removed. Note, the interlock above the door detects that the door is now closed. The door key that we have just removed fits into a key exchange control box. This ensures an exposure can't be made unless the doors are closed and locked. Below this is the control box, which is used to start and stop an exposure. On the wall above the key exchange box is another 3-light warning system indicating the bay status. Moving around the bay, we see another 3-light warning system and the source wind-out motor that is controlled from the main control panel. This motor operates control cables that pass through the wall and connect to the source projector. In this way, the Iridium-192 source is moved into the exposure position and retracted to the safe position. In the event of a power cut, the motor drive will not be operable. In this situation, it is possible to wind the source back in manually by attaching a winding handle. This handle is not normally present and must be physically configured to work. This is a safety feature to prevent the accidental manual movement of the source. Moving further round the bay, we see the second door to the enclosure. This door is closed and locked with a different removable key. This is to ensure that both doors are closed and locked prior to exposure. Again, an interlock is provided to signal that the door is closed. Next to the door is another illuminated warning sign. We will now see the order of events that happens when an exposure is made by a highly skilled radiography contractor. Typically, only one door will be used, so that keys B and C are in the key exchange box. Key A will have been used to open the door for setup and removed when locking the door. Key B is the key for the second door, and key C is required to operate the control panel. Key C cannot be removed until both keys A and B are in the exchange box and turned. Once key C has been removed, keys A and B become immobile and cannot be removed. They are therefore unavailable for use to open the doors and re-enter the bay while holding key C. Once key C has been removed, it can be used to enable the control system. Notice that the yellow safety circuit light is illuminated. This means that all the interlocks are made, all doors are shut, and the emergency pull cable is set ready. If any safety feature is not in place, then this safety light will not be illuminated and the source cannot be exposed. To make an exposure, the time of exposure is set on the control box and the green button pressed. The exposure time can be overridden at any time. After the green button has been pressed, a warning will sound for about 5 seconds. During this stage, the amber radiation imminent signs inside and outside the bay are illuminated. After this, the motor winds the source into the working position. The illuminated signs show the red radiation exposure state. The external key C panel and the internal radiation monitor both also show a red light to indicate exposure, and the control panel itself has an LED indicator to show the amount of source wind out. It should also be noted that the source stored indicator is off. The exposure can be stopped manually by pressing the red retract button on the control box. Exposure is stopped when the source is withdrawn back into the projector. When this is achieved, all the exposure lights are extinguished and the system returns to the safe indication state. In order to re-enter the bay, key C must be removed from the panel and returned to the key exchange box. This disables the control panel and allows removal of a door key. There are situations where the exposure will be stopped automatically. For example, if the emergency safety cable is pulled or any other interlock has been broken, such as opening a door. In such cases, a bell will sound. This bell does not indicate that there is a dangerous condition outside the bay. However, it does indicate that some action should be taken by the radiography contractor. In the case of a total loss of power, the source will be retracted into the safe position manually. Before allowing general entry, the experienced radiography contractors would then retrieve the door keys, as in a normal stop, and open the door to investigate. They would carry a radiation monitor to carefully check that the source was safe. The Radiation Protection Advisor, or RPA, has worked with the company and radiography contractor to ensure that exposures outside the bay are minimised, meet the ALARP principle, follow best practice, and are to all intents negligible. There is no such thing as zero dose, zero risk, and like all other workplace hazards faced by employees, residual risks are managed to levels that are satisfactory, and in this case, very low. For all reasonably foreseeable circumstances, the walls of the bay shield direct and scattered radiation to background levels outside the bay. Further shielding is provided by the wellhead material and the shielding canopy, which is moved into position for all radiography shots regardless of wellhead material thickness. There is, however, a small amount scattered from above the bay. The RPA has assessed this by considering a critical person who might be welding at 2 meter height on the welding platforms adjacent to the bay for 2,000 hours a year. The critical person is not real, but allows the RPA to demonstrate that even if that person did exist, the potential exposures are within limits. The assessment shows that this would be less than 200 microsieverts per year. This represents less than 20% of the annual public dose limit. It is less than 1% of the annual employee dose limit and less than 8% of the radiation exposure received by an average person in Scotland from just living for 1 year. In this assessment, radiation from radon, cosmic radiation, medical X-rays and foodstuffs are considered. To further put the dose into context, the maximum rate of dose accumulation of the critical person is less than 6 microsieverts per hour. This is comparable to the rate of dose accumulation from cosmic radiation when flying at 37,000 feet in an aircraft. The difference is that the flight might potentially last for hours, whereas such an instantaneous dose around the bay would only last a matter of minutes at the most, and would be unlikely to be repeated frequently. It should also be noted that the critical person is assessed under a number of unlikely scenarios, such as the shielding canopy not being used as intended, or a higher activity source being used. It therefore should be recognised that this is very much a worst case assessment. For the more realistic scenario, annual employee dose from the potential scattered radiation outside the bay are indistinguishable from background radiation.